It's great to be here. It's a very happy day for everyone, but I'm guessing more for Neha, a special day. Before going through the norms of the rules of the game for today, I want to thank the committee for being here, especially John, because he was kind enough to step in as chair of the committee and an official MECI representative advisor to Neha while after I step down. So thank you for that, John. Okay, so quickly, I think this is still the case, but correct me if not. Neha will present for about 45 minutes, after which we'll open up to questions from anyone. So it's better if you keep your questions until the end of the presentation, unless it's a clarification, then it's a fair game. After that, the open session of questions. If the committee wants to, we'll have a closed session of questions with Neha. And after that, the committee will deliberate and we'll get to a final verdict of for the future of Neha. So no pressure. And then we'll celebrate. Whatever happens, we'll celebrate because this is a great day. Okay, so Neha joined the department in fall of 2019. She's been like an incredible force. And if I have to highlight one thing, is her degree of commitment and perseverance on an idea. Almost since the beginning, she's been pushing forward this idea that you can manipulate deformable objects. Could be cables, could be towels, could be other garments, in a much simpler way than having to fully perceive everything about the object. So combining the strengths of both vision and tactile. If I had to highlight one thing specifically about sort of that obsessive commitment, I would say there was one brilliant day, not in the best of times, where at the beginning of COVID closure, when Neha said, you know what, I want to continue doing experiments. Simulation is not enough for me, right? If I have to manipulate clothes, I need a robot. So we had to take a robot to Neha's apartment so that she could continue doing experiments. So that to me shows the level of commitment. So thank you, Neha. I'm very excited to hear your story today. It's a great journey. So please take the floor.
All right. Hi, everyone. Thank you all for coming today. So we're going to be talking about my research on deformable object manipulation using visual tactile perception and control. We'll cover the components that allow us to dexterously manipulate objects like cloths and cables in ways that were never seen before, like tracing along a cable and plugging it in using only tactile sensing, tracing the edge of a long towel, again, only using tactile feedback, picking a towel up, grabbing it by the corner, grabbing an edge, and tracing to the other corner so we can do tasks like folding the cloth. And finally, showing how we can transfer these skills to garments, where we can find good grasp regions on the table and in air, and to be able to fold and hang shirts. So many of the techniques in robotic manipulation have focused on rigid objects, but deformable objects are everywhere in the real world. Even limiting ourselves to 1- and 2-dimensional objects like cables and cloth, the applications are incredibly broad. From industrial automation, from clothing factories, to wire harness assembly, to packaging with flexible materials, to rescue scenarios and emergency response, to surgical robotics, whether we're suturing or handling deformable tissue. But perhaps the most compelling domain is assistive home and healthcare robots. So here, these environments are filled with deformable objects. And unlike industrial settings, you would want one robot to be able to do all of your tasks, from doing laundry to helping someone get dressed. That's where general reactive manipulation is really important. Deformable object manipulation is difficult because many of the techniques developed for rigid objects don't directly transfer for deformables. First of all, there's the issue of perception. Deformable objects are highly self-occluded, which means that folds and wrinkles often hide key regions of interest. Plus, they have an infinite dimensional configuration space, making representing your object or reasoning about the full state of your object especially difficult. They also have complex dynamics and high model uncertainty. So even with detailed finite element models, they're expensive to simulate and still unpredictable. Both of these issues complicate planning and control. Deformable objects are highly sensitive to constraints. So if you lose a contact point, the object configuration can change dramatically. This means that many tasks like folding or knot tying need some form of long horizon planning. But in order to do that, you need to know what state your object is currently in and how your actions are going to affect future states, which, as we've discussed, is extremely difficult. On top of all of this, there can be wide variety even within an object class. For example, cables of different sizes or rigidity, or how all these shirts are manipulated differently if you were to try to fold or hang them. So with these challenges in mind, let's take a look at related work. The majority of the literature is mostly limited to pick and place actions against a table, so common tasks include reshaping rope and cloth. These slow incremental motions can be treated as transitions between static states. On the cloth perception side, given how common self-occlusions are, much of the literature first focuses on flattening the object before proceeding with other tasks. Some works try to keep track of the global state of your cloth or learn global dynamics models for specific actions, but these are computationally expensive and often unreliable for deformable objects. On the other end of the spectrum, task-specific learning can be quite successful on challenging tasks, as seen in this behavior cloning example on the left. However, data collection is extremely expensive. These behaviors in particular needed thousands of expert teleoperated behaviors demonstrations, and the learned policies don't necessarily generalize. So what's learned in perception, planning, and control often fails to transfer to new tasks, out of distribution objects, unexpected failure modes, or variations in scene layout. And that brings us to our work. So our key goals are to build a system that can manipulate cloths and cables or deformable objects in general in real time, or at least as efficiently as possible to start to approximate that, is reactive to perceptual inputs, disturbances, and can recover from failure, and is generalizable. We don't want to limit ourselves to specific tasks in our hardware, perception, or control strategies. We want our techniques to scale to different objects within a class. So we're not able to perform these tasks as fast as humans yet, but by approaching them more like humans do with a wider range of manipulation skills and perceptual abilities, we can reduce the number of steps. It currently isn't feasible to do manipulation quickly while mapping out the global state of your object. And we'll cover how we get around this by shifting from a global to a local perspective. We do this by combining visual and tactile perception. So vision gives us global context to figure out where to grasp and what action to take next. But for fine-grained control, we need tactile sensing, and that's where gel sight comes in. So here we have this sensor where the deformation on the gel surface of the fingertips gives us information on contact shape as well as normal and shear forces. This tactile feedback allows us to do things like slide along the edge of a cable or trace along the edge of a towel by estimating the pose inside the gripper. We can also apply tension through shear and verify whether or not we've successfully grasped a point of interest. We design our visuotactile system to be modular and generalizable. Rather than building task-specific networks, we use interchangeable perception and control modules that work across different objects and tasks. And by acting on local constraints, our system can perform complex multi-step behaviors while staying reactive to what it sees and what it feels in real time. So this talk is going to cover cable sliding, cloth sliding, visuotactile affordances and its applications towards towel folding, dense correspondence, and we're going to combine these last two for a confidence-aware in-air garment manipulation system. Let's begin with cable sliding. So we've developed a framework using only tactile sensing that successfully slides along a dangling cable without any added mechanical constraints. This video shows the full task from cable sliding to insertion. And this is our experimental setup. We have one fixed gripper and one moving gripper on a robot arm, and we use the tactile signal of the moving gripper, which is the one that slides along the cable, as input to our controllers. We're going to be focusing on the perception and control modules of the following system. So for perception, we're able to reconstruct the depth image from the tactile image, threshold to get the contact region, and then perform PCA to get the principal axes of our contact ellipse, which we use for our pose estimate. The area of this contact region is also used as an indication of signal quality. So a larger area means you have a better signal, while the displacement of the markers is used to approximate shear. If this is too high, then it's difficult to slide along the cable. So we use this pose as input to our pose controller, and we use the contact area and marker displacement as input to our cable grip controller. These two controllers are completely orthogonal to each other, allowing them to be decoupled. Our grip controller operates normal to that given plane, while our pose controller moves along it. Starting with our grip controller, we have two main goals. First, the friction force must be reasonable enough for sliding. So in this case, on the bottom right, the gripper is pressing too hard and there's too much friction to slide. And second, we want the tactile signal quality to be maintained. So here, the gripper isn't pressing hard enough to get a clear enough pose signal. Controlling our gripping force is essential, especially if we want the controller to work for different cables. We made a specialized gripper for this task that is able to modulate gripping force at 60 Hz to be able to adapt in real time to these signals. Moving on to our cable pose controller. So this figure shows the cable between the two grippers intersecting with that highlighted plane. So for our first baseline controller, you could slide along the cable open loop, but kinks in the cable or external disturbances could mean that you slide off really easily. So as a slight improvement, we're going to introduce this variable y. So this is the offset of the cable from the center of the grip, and we use it such that if the magnitude of y ever gets too large, we can recenter our grip by moving the moving gripper towards our fixed gripper and regrasp. So open loop with regrasps is our second baseline controller. And as you can see in this video, every time the moving gripper comes back to the fixed gripper, it's performing a regrasp. You can see how the cable is recentered within the grip. A slightly more sophisticated proportional controller can change your pulling angle phi proportionally to the cable offset in y. Here, the colors we choose to use are red for our control variables, this is the pulling angle phi, and green for our state variables. We already have y, we're going to add theta, the angle of the cable within the grasp, alpha, so this is the angle between your two grippers, and we want all of these state variables to go to 0, so you have a centered straight cable in the target state. Since the deformable gripper has complex friction dynamics, we use a data-driven method to learn a linear dynamics model for our system. We use a proportional controller plus some noise to collect data. So we use linear regression to relate each of the state velocities to the state and the control input, and then use this linear dynamics model in a linear quadratic regulator or an LQR controller. These graphs show the predicted versus ground truth state velocities of our linear models for y dot, theta dot, and alpha dot. So in these bottom graphs, we compare LQR to our baseline controllers. The two metrics I'm going to highlight are the distance traveled overall, normalized by the length of the cable, and the distance traveled per regrasp, normalized by the maximum workspace of the moving gripper. So the larger this distance per regrasp value is, the fewer regrasps are necessary to traverse a cable. All of our controllers with regrasp are able to consistently travel the length of the cable, highlighting the importance of a timely detection of when the cable is about to fall. More importantly, the LQR controller outperforms all our baselines in terms of distance per regrasp. So the robot can consistently follow 1 meter of cable within 2 to 3 regrasps. Also, we talked a lot about generalizability earlier, and even though our dynamics model was trained with a single cable, the orthogonal grip controller allows the cable pose controller to be applied to a variety of cables, with different properties like size, texture, and rigidity, using data only collected with a single cable. And here we show that we can still follow the cable in real time in the presence of disturbances. In order to do the plug insertion part, we determine the pose of the plug, adjust the gripper to account for pose mismatch, and then plug it in. And once again, here's the whole process put together from sliding to insertion. So we've shown that we're reliably able to slide along a cable within our framework. So now we're going to use similar techniques as we did with cable sliding to trace along the edge of a towel. Here's our experimental setup for cloth. In early trials, we found this to be a significantly harder problem. And you can get a sense for how hard this is if you were to try to follow the edge of a towel with just 2 fingers. So humans usually do this task by using multiple fingers to help constrain your object. So to help account for this, we modified our setup. The stationary gripper is now the one with the tactile signal, while the other gripper pulls the cloth through. And this is done under tension, and this is flipped from our cable following setup. So the biggest challenge that we encountered was the cloth falling out of the grip. And to emphasize this problem, if the towel ever reached the point where less than half of it was in the gripper width, then it would quickly proceed to slide out. And compare this to cables where halfway through the gripper was our target state, which made learning a controller for cables a lot easier. Also, regrafts are much more complicated for cloth due to the additional dimension. So unlike our cable experiments, we don't use regrafts for cloth sliding, and we also don't implement a grip controller. We tried to directly translate our previous model-based approach to cloth, and we ran into 2 key problems. First of all, this is what our cloth tactile images look like. Since the towel distributes pressure onto the gel surface, unlike the more concentrated cable imprint, the contact region is harder to distinguish. So this more colorful region is where your towel is, and in general, the towel edge can be identified by the leftmost close to vertical green line. So this red line you see is the hand-labeled towel edge. Everything to the right of this edge is in contact with the towel. And as you can see, it would be hard for even a human to consistently identify the edge. So from this, we decided that we needed softer gels on the tactile sensor for increased sensitivity. So here is the edge of this image. We tried using a model-based approach like we did for cables, using filters and canny edge detection, but we had issues because of the increased wrinkles from the softer gel, as well as mistaking the towel hem for the edge. So instead, we decided to use machine learning. So here we use a tactile depth image as input, you put it through a convolutional neural net, and get the pose estimation and cloth classification as output. So breaking this down, our cloth classification output is whether we see no fabric, an edge, or all fabric. And if we see an edge, the pose output is defined by the center coordinate and rotation angle of the line. So how do we make our data set? So we start out with a hand-labeled training image. So the hand labeling process is quick. I just click on 2 points that define the line for the image. Then we get the depth image and augment it by modulating the maximum depth. Then we further augment the training set by translating and rotating the image, and the label plus add some noise. So we had 150 hand-labeled training images, which we were able to augment to 30,000 depth images for our network. And here's what our network looks like in action. So as you can see, it's robust to strong wrinkles because the training set included wrinkles, and it's still able to identify the fainter edge when the towel is off to the right. And this faintness is because of the convexity of the gel surface, so there's less pressure on the outside of the gel. And it's also able to identify the cases where there is no fabric on the sensor surface, as well as cases where the sensor is completely covered in fabric. So moving on to our pose controller, we once again want to learn a dynamics model relating our state velocities to the control input phi and our current state defined by our cloth offset y, the angle theta within the grip, as well as the angle between the 2 grippers alpha. Note that now y is defined from the inside edge of our gripper because our target state has shifted for cloth. So once again, we collect data using a proportional controller, learn a linear dynamics model, and use LQR to follow the cloth edge. So now if you start at the ideal starting point, so all the way on the inside of the gripper, the LQR controller, based on the linear model, consistently traveled the entire length of the workspace in all of our trials. And we were once again impressed with how well the linear model worked. With a different starting condition, however, so especially starting with the towel edge at the center of your gripper away from the target state, the robot traveled an average of 76% of the workspace, or 43 centimeters. So we've shown that we can consistently follow the cloth edge, but only if you hand feed the towel in an ideal starting grasp on the edge. So how would our robot be able to do this task with a towel on a table? And that transitions us to our next section, visuotactile affordances for cloth manipulation with local control. Starting with the motivation for our task, as humans, when we manipulate long cloths like a towel or a bed sheet, we often want to grasp the cloth by adjacent corners. But how do we get to the corners? Many works use solely vision to find adjacent corners. But since the cloth often occludes itself, a common first task is first flattening against a table, and this is often done with incremental pick and place actions. But these techniques have been rather slow. In addition, the cloth might not be directly graspable. The corner might not be directly graspable, as you can see in this case where the corner is folded in towards the cloth. This is where the sliding skill can become particularly useful. Our system can pick up a towel from the ground, it grasps the corner, and then we introduce our novel visuotactile grasp affordance network that we use to grasp an edge. It can choose between grasping or rotating until it can find a good edge grasp. Once the robot grasps an edge, it can slide on the edge under tactile control until it reaches the corner. Once it grabs the corner, we can do other tasks like folding and unfolding. We're going to be discussing 3 key capabilities that are necessary to generate the complete behavior. So first, tactile perception of local features. Second, visuotactile affordance for grasping edges. And third, tactile sliding. So to give these modules a little more context, the visuotactile affordance network takes the depth image from our RGBD camera as input and outputs an affordance heat map. So the red colors indicate locations that are predicted to result in a successful edge grasp. So a successful edge grasp is more complicated than just finding an edge segmentation. This means that we need a single layer of fabric with a visible edge in the gripper's tactile signal after going in with a side grasp. So if the network were just to output an edge segmentation, it's also highly likely that the gripper would collide with other fabric on its way towards the edge or not be properly aligned with the surface normal of the fabric. We train this affordance network using tactile supervision. So the robot attempts a grasp and the tactile image indicates whether or not an edge was successfully grasped. Once we've grasped an edge, we can slide to the corner. We use shorter towels in this project so we can slide downwards where the towel's in a relatively stable configuration the entire time. So let's start with our tactile perception networks. So like we covered earlier, in order to slide, we use tactile sensing to estimate the pose of the towel edge within the grip. This network takes a single tactile depth image as input and outputs the grasp state, including whether or not an edge is being grasped and the pose estimate of visible edges. Here's another video showcasing this network's behavior. It runs in 33 Hz, and you can see that it's robust to wrinkles on the sensor's gel surface. We also have a separate tactile perception network with similar architecture in order to supervise our grasp attempts. So this network needs to distinguish between edges and folds, which can look really similar in the final tactile images. So therefore, we use multiple sequential images to capture temporal information. This network can also be used to differentiate corner grasps. For the purpose of our system, this grasp supervision network is mainly used to distinguish between edge and non-edge grasps. We use the same data augmentation pipeline. So for the sliding network, our pose data set consisted of 150 hand-labeled training images, which we augmented to 30,000 images. The grasp supervision data set covered here has 330 grasps per category, which we augment to over 6,000 per category. So here we show our grasp supervision network classifying between an edge, all fabric, a corner, a different edge, no fabric, and different folds. So moving on to our affordance network, in order to find the best edge grasp point, this network takes a depth image as input and then uses a UNet architecture to output an affordance heat map. So in simulation, we can label the entire image, but there's a sim to real gap. On the robot, we can only test one grasp point at a time. So our method uses both strategies. We first train in simulation and then fine-tune on the robot. The affordance labels can be calculated in simulation because we have access to the full state of the cloth. Good affordance occurs when the cloth point is an edge, is just a single layer, and can be grasped without collision. So the single layer metric is based on ray tracing. Collision free is mostly about the surface normal, so will the cloth fit inside the gripper opening? And reachable is whether or not you're on the right side of the cloth where the robot arm is. Then we fine-tune this network on the real robot. Instead of explicitly checking all the labeling criteria needed in simulation, we are using tactile supervision from the grasp attempt to self-supervise if an edge was successfully grasped. We collect 3,000 grasps for fine-tuning. And here's our network in action. It's able to distinguish between edges as well as folds, and cases where the gripper would collide with other cloth regions or grasp multiple layers. And here are examples where the entire right edge is graspable. The right side of the image is actually a fold. In cases where the edge is twisting in and on itself, such that only parts of it are graspable. So in this one, only the top half of the edge is graspable because the bottom twists in on itself. And in this last case, the surface normal is only aligned to the gripper at the bottom. So we compared our network, so this is the fine-tuned affordance shown in the middle, to 3 baselines in total. So the first uses edge segmentation based on work from CMU that takes in a depth image and outputs a segmentation of the edges. We consider edge uncertainty, reachability, and surface normal alignment of the gripper on top of the edge segmentation. But this approach can't identify grasps that would fail due to collisions with other regions of fabric. Next, the network trained directly from simulation without fine-tuning is too conservative and often misses grasp opportunities and completes a full rotation without any successful grasp attempts. And finally, our network trained directly on the 3,000 real grasp attempts is more likely to grab inside the cloth without the underlying structure from simulation. Ultimately, our network outperformed the others both on our offline evaluation set and during real robot deployment, requiring fewer grasp attempts to grasp a real edge. So now that we can grasp an edge, let's cover tactile sliding in this new configuration. We have tactile sensors on both grippers, so the pose from the sliding gripper informs the controller whether to move forward or back to move the edge towards the target state. When the other gripper feels an increase in shear, the robot knows that it reached a thicker corner. Because of our high-resolution pose estimates, we're still able to slide to the corner even in the presence of disturbances. Now that we can grasp adjacent corners, we can move on to folding. Since we know the size of the towel, we can do tasks like folding open loop. Visuotactical feedback can be added to accommodate towels of different shapes and sizes, as we'll touch on later when we come to folding shirts. And just to sum up this project, because we've introduced a lot of new components, we've developed a tactile perception system for estimating the pose of the fabric edge for tactile sliding, and classifying grasp types to tell if we've successfully grasped an edge. We've also introduced a novel visuotactile grasp affordance network for grasping edges, and we show how our tactile controllers can be used to slide along a towel until reaching a corner. And ultimately, we demonstrate how all of these components, using visual and tactile perception and control of local features like corners and edges, can be used together in a cloth manipulation system for tasks like unfolding and folding. So now we can find graspable edges on a towel, but how do we find other features on clothing items with more complex geometries? And this is going to bring us to our next section, dense correspondence. We use dense correspondence to match individual pixels between different configurations of shirts. So during training, we query a pixel on a deformed shirt and predict a probability distribution over the canonical flat shirt. This network is trained in simulation. On the robot, we invert the process. We query a semantic point on the canonical shirt, so this can be like a bottom corner or a shoulder, and we predict where that point lies on a deformed shirt as seen by the robot. What's novel about our approach is that we're the first to compute symmetry and confidence-aware dense correspondence for garments, both on a table and in air using a single unified representation. So symmetry awareness means that the network recognizes when multiple matches are valid, like your left and your right sleeves. Confidence awareness tells us when the prediction is uncertain, or the feature might be included so that the robot can react appropriately. So we train this network in simulation with a custom, detailed, parametrizable dataset generated in Blender. Our shirts have different colors and textures, U-necks and V-necks, differently sized collars and bodice dimensions, can be short sleeve or long sleeve, and feature details like seams. We found that the shoulder hem provided crucial context to help distinguish sleeve ends from bottom ends. We're able to include all of these features because we had scalable meshes. So each vertex on the mesh always corresponds to a consistent point without an intermediate skeleton as used in other works. We also randomize cloth dynamics parameters like stiffness and damping. Note that our dataset only uses a single frame of this animation, but the artifacts you see here from pushing the physics parameters to simulatable extremes gives you a sense of the limitations of current simulators for deformable objects. And here are some examples of our simulated dataset. We have 3,000 hanging images and 1,500 table images. The table dataset is in line with the level of difficulty of similar works. No one, however, has published on dense correspondence and hanging garments before, let alone a network that can find correspondences both in air and on a table. The shirt is highly occluded in most of these cases, and it's hard to find distinguishable features even as a human, highlighting why having a low confidence option is so important. So moving on to our network. So here we have a deformed shirt and a canonical shirt, and we're trying to learn pixel-wise correspondences between them. So during training, we query a pixel on the deformed shirt, and we're able to get the corresponding pixel match in simulation. We put these images into a dense correspondence network that we're training. The output of this network is a dense descriptor for the shirt, where every pixel is mapped to a d-dimensional embedding, capturing some notion of the location of the pixel with respect to the canonical shirt in descriptor space. So how is this network trained? Traditionally, these networks are trained with contrastive loss. Here we find pixel matches between the deformed and canonical images and structure the loss to decrease the distance between matches in descriptor space. Simultaneously, the network finds non-matches and pushes them further apart. For distributional loss, we have a target distribution that's a multimodal Gaussian with modes at symmetric match points. We get the probability estimator by taking the softmax over negative distances in descriptor space. Then we train the model by minimizing the difference between your target distribution and your probability estimate, as measured by KL divergence loss. Distributional loss is advantageous because we can encode symmetries and have a built-in confidence estimate, both of which are essential for in-air garment manipulation. And coming back to the slide, let's summarize the key contributions behind our dense correspondence network. It's the first to provide symmetry-aware and confidence-aware correspondences for garments, both in air and on a table with a single unified representation. And this is enabled by our parametrizable shirt dataset, which generates thousands of richly varied examples with consistent mesh correspondences across different shirt geometries. And we train with distributional loss, which models multiple valid matches and produces built-in confidence estimates, both critical for reliable reactive manipulation in complex occluded scenarios. So now that we've introduced our visual grass selection tools and our tactile perception capabilities, let's see how they come together in a unified system for reactive, confidence-aware in-air garment manipulation. First, we change our grasp affordance network to look for any successful cloth grasps instead of just towel edges. So in SIM, we explicitly check some of the same criteria, including, is the point reachable with a right side grasp? Will the gripper collide with fabric on its way over? But now, instead of the single layer constraint, we're interested in, are we grasping 2 layers of fabric or less? Or are we accidentally grasping more than that? We once again see issues with sim to real transfer because the shirts in real life have a wider range of material dynamics that we're able to capture in simulation. So we once again fine-tune on the robot using a tactile classifier to self-supervise grasp success. Here we show the data collection procedure for fine-tuning. The visualized grasp affordance shows predictions for the model trained in simulation, and we select grasp based on that affordance in order to improve efficiency of grasp selection while we fine-tune. We also visualize the results from our grasp classifier network that we use to supervise the success of grasp attempts. In simulation, we're able to label affordances for entire images, and we trained with 3,600 different images in sim. On the robot, we evaluate a single pixel at a time. We fine-tuned with over 8,000 grasp attempts, all self-supervised by the tactile classifier. We found that this was definitely a harder problem than just finding a towel edge grasp, especially because we're interested in affordances for a broader range of material dynamics. So here are examples of our fine-tuned affordance network, so that the one all the way on the right, compared to the one only trained on simulated images and the one only trained on 8,000 real grasp attempts. We found that our network from simulation was too conservative, often missing important points on the bottom of the shirt, likely due to the sim to real gap. While training only on real data resulted in overconfidence in unexplored areas. All right, so we've modified our affordance network for general cloth grasps. Let's incorporate this into a larger confidence-aware system for in-air garment manipulation. So breaking down our framework, we start with picking up a shirt from the ground using dense correspondence and use tactile sensing to ensure grasp success. We pick a second point in air using dense correspondence, but now we include grasp affordance to ensure that point is actually graspable. And once again, our tactile classifier lets us know if the grasp was successful. If a grasp doesn't have enough fabric, then we can just try again. Once we have two grasps, we can tension the shirt with tactile feedback, making manipulation generalizable to shirts of different geometries and to different grasp points. And finally, we can either fold or hang the shirt on a peg. So here's a step-by-step example of our in-air dense correspondence plus affordance system for a single grasp. So in this case, we're querying a point on the end of the sleeve, and this is the best correspondence match according to the network. I know it's incredibly hard to tell, but the robot is right about that point being a sleeve. Here's a heat map showing the probability distribution. So we're going to iterate through a video where the network decides whether to grasp its highest confidence graspable point, or if it's going to rotate to a new viewpoint. So over on the right, we're going to be visualizing the best match pixel, grasp affordance, correspondence to the sleeve, where darker red points are more confident, and finally, correspondence masked to points that are actually graspable according to affordance. We start with relatively bad affordance for the sleeve, since the surface normal isn't aligned with the gripper. As we rotate, the sleeve moves to a better position for grasping, and the network also becomes more confident that that point is indeed a sleeve. Once a high correspondence point has good affordance, we can go in for the grasp. So let's go through this in a state machine format. In order to find a grasp point, we need to check for confidence. So here we're checking for correspondence confidence as well as grasp affordance. And if these two are high enough, we can go in and attempt the grasp. And we only move on if the tactile classifier confirms grasp success. Otherwise, we can rotate and try again. So let's put this in the larger context of folding. We start by grasping a key point from the table. Now we're checking for correspondence, being within the robot's workspace, and that the tactile classifier confirms grasp success. We can grasp, if that point is successful, we can grasp the next key point in air. And if we're successful here, we can tension and fold. If we can't find a good first grasp on the table, then we can pick a random point, and our first grasp occurs in air instead. Instead of looking for the same grasps each time, we allow our system to dynamically choose between different folding strategies, depending on which grasp it's most confident in. So this first grasp is attempted on the table, but if that doesn't work out, the next grasp are attempted in air. If your first grasp is a shoulder, your next grasp will also be a shoulder. If your first grasp is either a sleeve or a bottom, your next grasp is either a sleeve or a bottom, depending on what's visible and what's graspable. And once we have 2 points, we can tension and fold. If we can't find a good grasp at any stage, or let's say the cloth slips out of your grip, we can return to a fallback option and start over. So if we can't find a good table grasp, our fallback option is just grabbing the highest point. If we can't find a good grasp in air, then we rotate our cloth, or if we can't find a good point in air after rotating 360 degrees, then we just grab the lowest point. And this is going to help unfurl the cloth because you're likely grabbing a sleeve or the bottom edge. We tension using tactile shear estimates by tracking the displacement of the markers on the gel surface of the fingertips. This closed loop step is useful for generalizing to shirts of different sizes and to different grasp points on those shirts. And here's a full example of folding where we show the tactile classifier after grasping from the ground, correspondence, affordance, and correspondence masked with affordance, tactile classification, tensioning, and folding. And here's a compilation of other successful folding videos. There's a variety of shirt geometries, including a long sleeve shirt on the top right. There's different material dynamics and thicknesses. You can see different folding strategies, as well as grasps being attempted and the tactile classifier telling the robot to try again. In addition to folding, we can use the same correspondence and affordance system for hanging. This time we look for a shoulder or collar point on the ground and look for a collar in the air. Then we bring the shirt over to the peg, pull down, and let go. Note that we can also do these tasks on long sleeve shirts because our dense correspondence network was trained to recognize different shirt geometries. Ultimately, we present a reactive visuotactile system for garment manipulation that integrates dense visual correspondence, visuotactile grasp affordance, confidence-aware planning, and tactile feedback. Unlike prior work that was constrained to tabletop manipulation or reliant on flattening, our system supports in-air garment manipulation by searching for correspondences directly from highly occluded states, enabling more flexible human-like manipulation. Additionally, our dense correspondence can be used as an intermediate representation for other planning modalities, which I believe is a super promising research area for future work. For example, we can learn from human video demonstrations. So here we're tracking hand skeletons and classifying gestures, looking for frame transitions to two grasping hands. From our keyframe, we can go back a couple of frames to get the unoccluded query point, calculate a probability heat map, and get the best pixel match. We can do this with the other point as well. Our dense representation could also be used as an intermediate representation with vision language models. This recent work uses language-conditioned imitation learning for clothing manipulation from flattened configurations. In contrast, our representation could be used to identify grasp points in more complex states, including in-air configurations where humans intuitively often find grasp points. This opens the door to learning not just from teleoperation or from simulation, but potentially from internet-scale human video demonstrations, where garments are manipulated in natural, unconstrained ways. I've also been interested in how our visuotactile representations could support symbolic planning. We've developed a library of tactile-enabled skills like picking, tensioning, sliding, and wrapping that operate over local constraints and don't require full state estimation. Once we tension the object between the grippers, we can control its configuration, meaning we know exactly where every point lies along that span. This makes local skills ideal building blocks for task and motion planning, where we can reason about how to chain actions together based on their effects on local constraints, rather than trying to model the global cloth state, which is often intractable. What's especially powerful is that our dense correspondence model provides a continuous object relative coordinate system, even for crumpled or occluded garments. Combined with tactile feedback, this gives us the foundation for symbolic planning grounded in real continuous execution space. And to wrap things up, let's return to our core goals. We set out to build a system that's real-time, reactive, and generalizable for manipulating deformable objects across a range of challenging scenarios. At the heart of our approach is this global to local framework. We use vision to provide global semantic context, and we use tactile for local precision. We demonstrated this across multiple tasks, including in-hand cable following and plug insertion and towel edge tracing, all using only tactile feedback. And then we incorporate vision for in-air folding of towels and shirts using dense correspondence and visuotactile grasp affordance for confidence-aware grasp selection. Together, these components allow for modular reactive control in challenging tasks, pushing deformable object manipulation towards generalizable, scalable, and real-world deployment. And before we get to Q&A, I want to take some time to acknowledge some special people throughout this journey. So first of all, I want to thank my parents for being so loving and supportive and prioritizing my education every step of the way. They really helped foster a love of learning and intellectual curiosity that led me to where I am today. I also want to thank the rest of my family in India who's currently listening, even though it's really late there, who have been my biggest cheerleaders for every milestone in my life, and it really means the world to me. I want to take a moment to shout out some of the communities that I found a home in here. I think grade school me would have been blown away by grad school me for singing in a band and teaching yoga and starting an acro yoga club. And I really wanted to thank everyone who has been a part of these groups and supported them and made them so fun to be a part of. I also want to say thanks to all the wonderful friends who have supported me through the past 6 years. There have been plenty of ups and downs throughout the way, and honestly, I couldn't have done it without you guys by my side. Thank you for the laughs, the dancing, the international trips. I'll truly treasure these moments forever. I want to give a special shout out to my boyfriend, Peter. Thank you for keeping me grounded, cheering me on, keeping me fed over these couple of months. I really appreciate your love and support and the joy you and your family bring to my life. Next, I want to thank members of the M-Cube Lab. They're a bunch of really smart, really incredible people who I've had a lot of fun working with over the past couple of years. And as the last official graduate from the lab, it's such an honor to have been a part of it. I want to thank the people I've worked most closely with, including C1, who took me under his wing when I first started in the lab, to all my other amazing co-authors, Sean, you, Arnau, Mega, who's here, Rachel, who helped me out with the planning line of research. I also want to give a shout out to Ted, who's been a huge part of our papers. And finally, I want to thank Alberto. When I first visited MIT, I wasn't entirely sold yet, but I remember having my first meeting with you and immediately after calling a friend saying, I think I want to go here. You've been an incredibly insightful and steady presence throughout this entire journey. Thank you for the constant support and encouragement, even when the problems we were trying to solve seemed impossible. I am grateful for the freedom you gave me in order to explore the research directions I was genuinely excited about, and how understanding you were for the times when life got in the way. It's been a privilege to learn from you and to grow under your mentorship. And thank you all for coming today. I'd like to open up the floor for questions.
Excellent work. I guess my question for you is, I mean, clearly, like the system that you constructed, like can do all sorts of things. But what I was wondering is, if you could choose a motion primitive that you could add to your system to like expand its capabilities, like what would be on your wish list?
I think something that would be interesting is interactive perception. I guess we rotate right now, but like it would be nice if we could do things like sometimes when we unfold shirts, we grab by the seam and then slide slightly, or we can push things out of the way instead of treating it like it's a rigid object when we rotate. So I think being able to explore more actions there, I think Tactile would be super useful for that, would be an interesting line of research.
That makes sense. Thanks.
Awesome presentation, Neha. This might be a bit of a naive question if it's already doing this, but I'm really interested to see is, have you given any thought to incorporating like time sequence data into the dense correspondence mapping?
Yeah, so for dense correspondence, we're currently limited to side grasps, right? So if we were to use correspondences across time, then when you move the cloth into a position where like maybe you lose some sort of correspondence confidence, but like you should be grasping now, that would be really useful to have a time element. I think there are ways to incorporate time directly into dense correspondence. The other way that we've thought about is maybe once you find a feature with high confidence, you could track it, but that only works if your cloth is rotating and, or I guess you could do it in two ways. You can expect that your cloth is rotating like a rigid object and track things geometrically, or maybe you track it with a more complicated tracking mechanism.
Thanks for the great talk, Neha. I was interested about what the intuition behind the fact that the affordances from simulation you said are too conservative. I guess I was expecting it to be the opposite.
Yeah, I've just assumed that it's because of this material transfer gap. I think that there are certain things with maybe how the cloth is falling that make certain shirts in simulation harder to grasp on the bottom. I'm not entirely sure what causes that, but it's what we've been seeing.
Thank you.
Great talk. I guess, so you were kind of constrained here in using this particular robot and these particular sensors. Do you think there's any hardware changes that would make this tracking easier?
Sure. So I do have a slide on this. So there are a couple different things that could make this problem a lot easier. So we could add more grippers, and so you could control more things because constraints are super important for this problem. You could add more degrees of freedom to your gripper, and so we played around with adding this pinching motion that really helped make it easier to grab an edge, for example. More cameras would probably do a lot. So right now we're limited to side grasps, but if we had a top view camera or if we had a gripper camera, we could probably approach the cloth from different angles. If we had multiple viewpoints, then we could probably use a different representation in order to find good grasp points for our cloth. Plus, another thing that we were really limited by was our workspace. So we were limited by, like, in terms of what actions we could actually do and how we could do those actions. A mobile base could let us do more interesting tasks, like getting laundry out of a washing machine.
Any other questions?
Congrats on your achievement. I noticed that the gripper on the right hand that was equipped with the gel site fingertips, that one did a lot of the action, but what did you incorporate for the other gripper? When we pick up objects and on any of the videos that you showed with people picking things up, there's a slight rotation of the wrist. Was that integrated into your model?
So we added, so the other gripper has most of the same capabilities as the first gripper. So it also has tactile perception and so tactile. So our system, we only showed it grasping from the ground and using tactile classification and then using the other arm and having tactile classification. But if this first grasp failed, then you would also do the same thing with the other hand, right? We also, both hands are capable of tracking tensioning by tracking shear. In terms of the rotation question, so currently what we did for our cloth system, mostly because of time limitations, was we rotate one gripper to straighten, right? So like you don't want to tension like this, you want to tension with both grippers facing the same way. So one, like how you should solve that is looking at where did you grasp relative to this other gripper and then rotate to fix that. We just rotated the smallest direction as a heuristic. Yeah, so I guess you don't necessarily need tactile for that, but I guess if you had like torsion, you could probably correct for that with your tactile signal.
Okay, we have one online question. Would you like me to read it?
Yeah, please. Okay.
So Rachel Holiday asks, first she says, amazing work and a beautiful talk. I'm not crying, you are. And then she says, mine's speculating on clothes that have non-fabric features such as zippers, buttons, or elastics, such as folding a fitted sheet.
So we experimented slightly with out-of-distribution shirts that had things like buttons and zippers and hoods. I guess this isn't specifically to the fact that they're non-rigid, but those objects, we found that the shirt was able to get like general understanding of the format of the shirt, but like, for example, if we had a sleeveless shirt, then all of a sudden the robot would think that maybe the bottom was the sleeve if you tried to query the sleeve. So it doesn't really understand when things are missing. But for more interesting motion primitives that you would need to in order to manipulate those objects, I think so. I guess there are different strategies. So the traditional like learning-based approaches currently would just require augmenting your data set to include more of that. And like, for example, the behavior cloning approach would require like specific demonstrations showing manipulation with that. I think there are certain abstractions that our research has that could allow us to generalize stuff that we've already learned to those kinds of objects. For example, like for a fitted sheet, you might need to tension, and we have the ability to tension. So the modularity allows for more flexibility when dealing with those kinds of new features.
All right, we'll do one more question and then go to the closed session.
Thanks for the great talk, Neha. And since I'm the last MCube person in the room who hasn't asked a question, I figured I'd just ask, what is the limiting factor for the speed of the system?
Sure. So right now, I guess the slowest stage right now is the rotations between different things. So we tried messing around with like the size of the rotation. So we decided that 30 degrees was the right amount to be able to see things the right way. I think if we had a different perception system, like maybe if we had multiple cameras, we would know exactly how much to rotate the object directly in order to be able to directly grasp something of interest. But in general, we're also moving the robot slowly so that the cloth stays stable, and so we're not shaking in between. So because otherwise we'd have depth mismatch issues. Yeah, those are currently our limitations with speed.